I'm hello everyone, and thank you for coming. I'm Leighton, and today I'll be showing you how I use orange components with the bacteria Bacillus licheniformis to form a biosurfactant that protects skin from microplastics. I just like to say thank you to Papa Jack for creating the K Fellowship and making this opportunity possible for me and my peers. I'm forever grateful for this experience, and it's due to your work that allows me to explore my passion in science. Microplastics are defined as plastics that are or less than 5 millimeters in size. Nanoplastics are defined as less than 1 micrometer in size. For the purpose of this presentation, I will use the umbrella term microplastics to encompass both micro and nanoplastics. Microplastics are produced in two different ways. One is through intentional manufacturing, with the purpose of them being in a product such as face scrubs or exfoliants. Another is unintentional degradation, where erosion and other forces of deterioration can produce them. These have been shown to cause concerns in other areas as well, due to pathways of entry into the body such as ingestion and inhalation. However, with our world being surrounded by plastics, contact with microplastics is inevitable. Polycyclic aromatic hydrocarbons, or PAHs, are involved in the manufacturing process and are adsorbed or coat the plastics through pollution exposure. PAHs are the harmful chemicals in things such as air pollution and crude oil. These can coat the plastics and make it more harmful when they enter the skin, with previous research illustrating skin irritation, inflammation, and disruption of natural skin functions. This can be solved through the application of a biosurfactant. A biosurfactant is a microorganism produced surface active agent, which helps emulsify oily substances through it both having hydrophobic and hydrophilic parts. The biosurfactant can emulsify the PAHs due to them being parts of oily substances in pollution and break down the PAHs into less harmful components. When Bacillus licheniformis, a bacteria I mentioned earlier, fed on orange peels, it allowed the production of a biosurfactant that broke down naphthalene, a type of PAH, and crude oil, which contains PAHs, into carbon dioxide. The reason why that study tested those PAHs is because they were found in mangrove environments due to pollution. The study also used orange peels because the bacteria need a substrate or a food to feed on to create the biosurfactant, and food waste such as orange peels is an eco-friendly and cheaper alternative uh, rather than expensive substrate, which is normally used to make biosurfactants. With this biosurfactant, I utilized it as a protective measure against harmful effects caused by microplastics on human keratinocytes, or Hakat cells. The reason why I chose these Hakat cells is because keratinocytes make up about 95% of the surface of the skin, so these cells would be most likely the first ones to interact with the microplastics. I intend for the biosurfactant to degrade the PAHs that are potentially in or on the microplastics to reduce the cytotoxic effects it causes. With making the biosurfactants, let's take a look at the anatomy of an orange. The skin, formerly known as the segment wall or the membrane surrounding the pulp, can be classified as orange skin. The orange pulp, including the juice part, is the orange pulp. The peel, which includes both the rind and the pith surrounding the outside, is the orange peel. These were all separated into their according categories, and a mixture of the components were also made as well. With these four components, they were made into four different biosurfactants. With all the components were dried until they are able to be pulverized into a powder. A blender was used due to the high efficiency of powdering these components. These powders were then packaged for later use. Then the powder was combined with LB broth, or media that helps the bacteria grow, along with the B. licheniformis. These flasks were then put in the orbital incubator to ferment at 37 degrees Celsius, which is around normal human body temperature, for 170 rotations per minute for 5 days to allow bacterial growth and metabolization of the specific orange component into the biosurfactant. After these were centrifuged to separate the solids from the liquid on top. Um, the liquid was then isolated and cold acetone was added in equal amount to the liquid produced to allow further purification of the biosurfactant. The acetone was then evaporated until the expected yield was reached. At the end of this process, I have created all four of my biosurfactants. While the biosurfactant was being made, the hot-cut skin cells were being cultured. We waited until these small specks of cells on the left transformed into a more complete tissue, where the cells grow and combine together. We wait for it to grow to this point, since it's an optimal time to test it because it ensures consistency in the experiments. Different concentrations of microplastics and media were based on exposure to real life, ranging from 0 milligrams per milliliter 0 milligrams per milliliter to 1 mg per milliliter. Middle values also included zero point 0.5 milligrams per milliliter and 0.25 milligrams per milliliter. Um, Media in these hot cut cells is what gives the cell culture a moist and nutrient-rich environment to grow. For this experiment, we measured cell viability to see if the hot-cut cells were alive and working. Cell viability was tested with an XTT assay through the ELISA machine, and it counts if the cells are alive through the specific wavelength of 450 nanometers, which higher levels show higher numbers of cell viability in the graphs I'm about to show you. I tested 4 biosurfactants at 4 different concentrations of microplastics with 4 replicates for a total of 80 wells. This was then replicated 3 times for the time periods of 24 hours, 48 hours, and 72 hours. In the first picture, it shows the cells in the plates that we tested them in, and the bottom picture shows what was in each well or in what was in each hole of that plate. Microplastics have been shown to cause damage to the hot cells in both 48 and 72 hours, as shown with the stars on top, relating to the lines in the control. This shows significant change. However, the lower concentrations seem to show similar cell viability at the end of the 72 hours, which is shown through the NS, or the no significant difference marker. Cell viability wasn't affected by the biosurfactants themselves, except the orange mixture, or the OMI biosurfactant at the end of the 72 hours. Just for context for looking at the rest of these graphs, let's go over the acronyms that are on the side of the legend. OPE is orange peel, OSK is orange skin, OPU is orange pulp, and OMI is the orange mixture. Um, in the 1 mg per ml of exposure of microplastics and the specific biosurfactant, all seem to keep the same cell viability similar to the control, except the orange peel and the orange mixture biosurfactants. However, in the 0.5 mg per ml of bioplastics with exposure to the biosurfactants, the only one that seemed to keep cell viability similar to the control was the orange skin, or the OSK biosurfactant. In the 0.25 mg per ml test, it had similar values to the 1 mg per ml test, and it wasn't really need to be shown due to the similarities. In the analysis of these assays, the orange skin biosurfactant has shown to work for all tests using the biosurfactant to protect against the harmful effects of microplastics. In all tests, the orange skin biosurfactant worked to keep the hot cells alive and in similar numbers to the control. This shows that potentially the orange skin biosurfactant can protect against the PAHs in and on the microplastics. Even though it's possible that it combats against the PAHs, a limitation of this study is that these microplastics were purchased directly from a manufacturer and weren't harvested through pollution. This matters because there was no PAHs for the plastics to absorb on, so the PAHs weren't gained through pollutive causes. However, it's still possible that there's PAHs in the plastics through the manufacturing process. For my further research, I will examine how the orange skin biosurfactant affects skin cell genes to see in the differences of what's being produced. This will be through RNA extraction and seeing the genes that are being expressed and affected. Overall, if you want to pursue a research project like this or anything related to your interests, I would recommend going through the K Fellowship. It's a wonderful opportunity to do more research over the summer. There are many amazing mentors there. One I would like to thank being Dr. Perez David. He has helped guide me through the process of both literature research and lab work, especially since it was my first time doing anything like this. I would also like to thank Dr. Chan, who helped with my initial research to join the fellowship and explaining many of the terms that I would now come to understand, and for even practicing this presentation with. There are more people who supported me in the lab to give advice, such as Mr. Hill and Ms. Kobayashi. And to my friends and family, thank you for supporting me and supporting me emotionally and letting me rant about my project. These are my references, and thank you for everyone for coming. Are there any questions?